The first question, what we need to understand general relativity? The answer to this question is the prerequisites for general relativity are simply advanced calculus, special theory of relativity, and the classical mechanics. These are the main topics necessary to understand general relativity. Now, next question, what are the references for general relativity? I'm just mentioning here the most famous references of general relativity is Introduction to General Relativity by Ronald Adler. But this is a book which is used as textbook in Stanford University. The second book is Gravitation. This is the thickest book you can see on science. It is that thick. By Mr. Thorne and Wheeler. There's many other books, the theory of space-time and the gravitation, general relativity, Einstein's essential survey, etc. However, I consider among these, there are others, but among these books, you can find a lot of books on general relativity. The first book by Adler, the second book by Mr. Thorne and Wheeler, and the third book, this is, I think, it is not easy to find even in Amazon. These are the most famous books on general relativity. Now, this book is edited. Edited, that means there are many authors writing this book. This is the first book I have seen. It is an Einstein essential survey, which try to answer certain questions, how to relate quantum mechanics to relativity. So this is the importance of this book. This is the first book that treats how to go from the physics of big universe to the physics of the micro universe. Okay. So in fact, these are the topics I'm going to cover very briefly during this lecture. The Einstein summation convention, free and dummy indices, canonical delta, and algebraic manipulation. I discovered that Dr. This canonical delta was used. Okay, I'll give you examples of this. Tensor notations for matrices, cardinal coordinates, the Jacobian, first, second, and higher order tensors, transformation laws for contravariant and covariant tensors, the metric tensor, lowering and raising of indices, derivative of tensors, covariant derivative, and the Christopher symbols. In fact, these are the basic elements I need for the next lecture, and I will explain certain of these, what is the physics of certain of these elements in a coming lecture. In fact, one says, how much we can cover in this course about general relativity? My answer is very little. We have only five lectures, and 5 lectures are not sufficient to cover general relativity. You have many solutions of general relativity. Each solution requires one complete workshop. You can imagine there are a lot of solutions. Of course, you will ask me how you can have many solutions of the same thing. In fact, in general relativity, you can have solutions, and each solution will give you something different. Here, the solution we will make during this workshop is for free space. If I have empty space, what is the solution of general relativity? This is what we the end of our course in general relativity. If you want to add not free space full of something, that is different. That will take a lot of time. It is beyond the workshop we are studying here. Okay. Let me go to Einstein summation convention. Usually, when I want to add terms A1, X1, A2, X2, A3, X3. Usually I use what we call the summation convention. The summation convention, sigma, the sigma here. Sigma, this is the what we use usually for summation. Now, the question is there another way to make the summation without using this sigma? We go to this example. If I look at this expression, I find I, J, K. These are different. There is no two indices which are equal. If I look at this term here, I find I is coming twice and J is coming twice. So in fact, this summation is simple. Whenever I have an index which is happening twice, I can make the summation on this index. Here I can make the summation, here I can make the summation, here I cannot. Now for example, let us take for n equal to 4, I have I, K, which is the same as this one. Now I can make the summation, I can make I equal to 1, I equal to 2, I equal to 3, I equal to 4. Okay? Why I make it I? Because this is happening twice. Here, the same. I have J is happening twice, so I can, for example, I want 4 terms. I put J equal to 1, J equal to 2, J equal to 3, J equal to 4. So in fact, whenever I have a repeated index, I make the summation on that index. Now, look at this term. Here I have J is happening twice, whereas I is happening once. If an index is happening twice, we call it dummy index. So a dummy index is an index which is repeated itself twice, not more than twice. Okay? Whereas I is happening only once. So this J, I call it dummy index. This I, which is happening only once, I call it free index. So in fact, I have two types of indices. I have a dummy index, on which I make the summation, which repeated itself several times, and I have free index. Now let us take this example. This is a simple example. I have, you can see here, I have I is happening twice, and R is happening twice. So I is a dummy index, and R is a dummy index. So what we do, in fact, to understand this, first we fix I equal to 1, and we take R from 1 to 3. Okay? I equal to 1, and this is 1, 1, 1, and R is running from 1 to 3. The same, I put I2 and I run R from 1 to 3. I put I3 and I run R from 1 to 3, etc. So this is the meaning of, so all these equations can be represented by this simple term. This is the idea of general relativity or the summation convention. I can in fact make very complicated equation into just simple term. So you can see all these equations are presented by this simple term. Now, as a summary, free index, I have usually the same range as summation convention, as summation indices. No index may occur more than twice in any given expression. That means, if I have an expression like, where is it? I don't have here. If I have an expression in which I have 3 indices, that doesn't work. Here, I have this one. This one I have I is happening 3 times. This doesn't work. Unless I put I, xi, it is xi squared. Now you can see I transfer this to an index which is happening twice. I is now happening twice instead of 3 times. 3 times doesn't work. Here it works. But generally, I cannot have an index happening more than 2 times. This is another example. Here I have I is happening 2 times. So this is a dummy index. And j is happening 2 times. This is also a dummy index. So in fact, I can make all these equations for n, in general for n term. All these equations can be represented by this simple one, simply by fixing one index and making the summation for the other index, etc. One may say, which one I start with? The answer is either of them. You can start with j equal to 1, and then you make I equal to 1, 2, 3, 4, 5, etc. Or you can start with I equal to 1, and then run j 1, 2, 3, 4, etc. So all these equations can be presented by this simple term. Now, chronicle delta, Dr. Shaban, I just noticed he write chronicle delta. I don't know if all of you know chronicle delta, but I will give you some simple example because chronicle delta is very important in general. So here, what is the definition of chronicle delta? Chronicle delta, you can see I can have 2 indices down, 1 index down and the other up, or 2 indices up. Okay? So if the 2 indices are equal, if I equal to j, then this is equal to 1. So delta 1, 1 equivalent, or delta equal to, or delta 1, 1, or delta 1, 1, all equal to 1. If these are different, then I will get 0. For example, evaluate this quantity. Now what I observe in this quantity? I observe that I is happening twice, and j also is happening twice. So in fact, I is a dummy index, and j is also a dummy index. So what I do, I make I equal to 1. Okay, so we have delta 1, xi1, and then I make j running from 1 to 3. Okay, this will give me one equation, and then I make I equal to 2 and j running from 1 to 3, etc. So in fact, all these equations, you can see all these equations are presented by this. But if I do here the summation, look here, delta 1, 1, these are equal, these are similar. So they are similar, this is equal to 1. So this term will give me x1, x1. This is delta 1, 2. So these are different, this is 0. Delta 1, 3, this is 0. This is 0. This is 1 again, because 2, 2, you have 1. So you have x1, x1, x2, x2. Here you have 2, 3, this is 0. 3, 1, this is 0. 3, 2 is 0. 3, 3, this is 1. So I have, now I recover this one, and that one. And so I will have x1 square, x2 square, and x3 square. And this is simply can be written xi, xj. Sorry, xi, xi. So in fact, this term here and all this is represented by this simple term. This will show you how this convention, Einstein convention, can make things easier, can make things simpler. Now let us take another example. I chose this example because it's very informative. Here, I have aij is a constant, and I want to take the partial derivative of partial by partial xk of these quantities, of this quantity. Now I observe here that I have I is etc. Domain index and J is domain index, but I don't need this. Now, if I take the partial derivative, of course, I say this is constant, so I can take it out of the derivative. Here, I will have what? I will have partial times k of the rest. And you know, by multiplication, you can have the first derivative, the second, then the second derivative, the first. Okay? And then, look, here I have jk. If j is equal to k, that means x by partial x is equal to 1. So I write it like this. Delta jk. If j is equal to k, this is equal to 1. Otherwise, it is 0. The same for this one. Delta j. Here, delta ik. Ik. Now, if I equal to k, this is 1. Otherwise, it is 0. So now I can just open this term. I will get these two terms. Aij, this is constant, of course. Ai, xi, delta, etc. Now, what I can do, I can make j equal to k. If I make j equal to k, this is equal to 1. So here I will present the j, I make it k. So this will be I, k, xi. Here, if I make I equal to k, okay, so this will be k. Okay, and this will be 1. So I will be left with these two terms. Now, how to add these two terms? Look here. I is happening twice. Okay? Is it? Yeah. I is happening twice. So in fact, this is a domain index. I can take it out, and I'm left with these two terms. Aik plus Aki. So in fact, this will show you how we use the conical delta to simplify equations. Now I will go to matrices. All of you know matrices, but this is very important in general relativity. In fact, the matrix we are using in general relativity is a 4x4 matrix. You know why?
4 dimensions of space.
Yeah, because we are talking about 4 dimensions of space-time. So in fact, here this is general, of course. This is general for n term. What is important is that the mn. Look here, the first one is the row, the second one is the column. For example, this one, 2, that means I have 2 rows. 3, that means I have 3 columns. Here, 4, 2, 4, that means I have 4 rows and 2 columns. Here, I have 1 row and 4 columns. So this is the symbols we are using for matrices. Now what is a vector? A vector, as Dr. Shaban said, it is a column matrix. A vector is a column matrix. So in fact, the number of rows is m. You can have as many rows as you want. But 1 column. You have 1 column. Now, whenever we are talking about general relativity, we usually talk about transformation from one coordinate system to the other coordinate system. I will call normal coordinate system and barred coordinate system. So when you see this bar here, this bar, this is the quantity in a bar coordinate system. And this quantity is in the other coordinate system. So I have xi coordinate system and I have x bar coordinate system. Now you have to be careful. Now this I is not an exponent. This I is not an exponent. Okay? This I indicate that I have 1 dimension, 2 dimension, 3 dimension, 4 dimension. Usually in generativity, I add from 1 to 4 or from 0 to 3. Okay, so I equal to 0, 1, 2, 3, or 1, 2, 3, 4. It depends upon the order. Okay, but in general, this I is not an exponent. It indicates the dimension. Okay, so here I have this function here. This is very, very important function. I have, this is a relation between a certain quantity and the barred coordinate system with respect to another quantity and the unbarred coordinate system. Okay, we write it this way. Okay, we go to curvilinear coordinate. We have two types of coordinates. We have rectangular coordinate system, x, y, z, that we know, and we have curvilinear coordinate. Curvilinear coordinate, how many curvilinear coordinates we have?
Infinity. You can have as many as you want.
Infinity. But the most important are these three. I'm going to talk about the polar coordinate system, the spherical coordinate system, and the cylindrical coordinate system. All these are curvilinear coordinates. Okay? I will just explain rapidly, and then I will give you as an exercise. And I want to tell you that all my lectures are available. You can take it. You can take a printout. Okay? Or you have a link. You can have. Okay, so anything I'm saying here is written in my lecture notes. We will give it to you. Okay? So my lecture notes are available. Now this is the polar coordinate system. As you know, polar coordinate system, I have to determine the position of a point, I use the r theta. Okay? R theta, and I have a relation between the x component, x equal to r cosine theta, and y equal to r sine theta. These are the coordinate, and you can see I put x1, x2. These are the components in the barred coordinate system, and these are the components in the other coordinate system. So I have x1, x2 are theta, but x1 bar, x1, 2 are xy. So how to relate these two? By these simple equations. Okay. Then x here, look, I write it as x1. R is unbarred x1. Cosine theta is x2. Okay. So this is how we transfer from one coordinate system to that coordinate system. This is just a notation. This is nothing. There is nothing about this. There's just a notation. How to write instead of r theta, I write it x1, x2. And this is the inverse transformation. Of course, you can, from this one, you add this one square plus that one square, and you will get these inverse. This is the cylindrical coordinate. In the cylindrical coordinate, of course, I have to determine the position of a point. I have three coordinates: r, theta, and z. R, theta, and z. Of course, there is a relation between rho. This is rho. From here to this point, this is rho, and I don't know why it should be visible. Okay. This is rho, and this is r, and this is z. So in fact, these equations can be written this way: x1, xy, z, x1, x2, x3, etc., which is r, theta, z. I go to another coordinate system. This is another curvilinear coordinate system. This is the most important coordinate system used in general relativity because it has spherical symmetry. I'm using rho, phi, and r as units, and you have all these relations written here for r, phi, and rho. Yeah, I'll come back to this. I'll come back to this later on. Jacobian, but I will not talk a lot about Jacobian. But Jacobian is given by this function, partial with respect to the coordinate system, between the bar coordinate system and the normal coordinate system. So in fact, this is a transformation equation because it relates a quantity in one coordinate system to a quantity in another coordinate system. This is a transformation equation. Of course, I can have general coordinate system instead of restricting myself to x1, x2, x3, x4, which is used by general relativity. I can have any other coordinate system. Okay, now we come to business. Now I'm going to talk about tensors. Of course, you will ask me the most important question, why tensors? Why we are using in general relativity tensors? Why we don't use normal vector? Why we are using tensors? Because a tensor, I will explain this in coming lecture, but usually that's a very rough idea. A tensor is a characteristic. If I have a quantity, I cannot express the quantity only by x, y, z, its position or whatever, 3 terms. This quantity could have many other characteristics. It could have certain temperature, it could have certain pressure, it could have certain density. So in fact, any quantity could be expressed by many other properties which cannot be expressed by a simple vector. Therefore, a tensor is very general. If I have a quantity, I can express anything regarding this quantity by a tensor. And these small things consisting a tensor, usually written in a matrix form, we call it component of a tensor. So in fact, a tensor, as we are going to see, is the right way to characterize any physical quantity. Now, there are many types of tensors. Let us read what is written here. This is a tensor. You can see where is the one up. 2 is up, 3 is up, n is up. Okay? And there is no bar here. There is no bar. This is a tensor in a coordinate n-bar coordinate system. And since this quantity 1, 2, 3, n is up, I call it contravariant tensor. And also I can observe this is only one number. This is one number. So that is why we call it first order. First order, coming from this part, is one number. One number, etc. And since it is up, I call it, this is contravariant tensor. And where is this tensor? In the xi coordinate. This is I is not exponent, this is the xi coordinate, which is x equal to, I equal to 1, 2, 3, etc. Okay? Now this one, the same tensor, but not in the xi coordinate, this is the x bar coordinate. Okay? So this is a first order tensor. Why first order? Because I have one number here, one number here, one number here. This is first order. And this is happening in a bar coordinate system. This quantity I call it a tensor. That is not a definition. That is a notation. Now, how can I define a tensor? Now, let us see what I observe here. I have this tensor is happening in the path coordinate system. And this is a contravariant tensor because I is up. Here I have a tensor which is in the unbound coordinate system. So I have a relation between a tensor and the bar coordinate system to a tensor and the unbound coordinate system. And how transformation is taking place? Taking place like this. I have the xi up, r down. In fact, this is the definition of a contravariant tensor. Whenever I have a contravariant tensor, this is I call the transformation law of a contravariant tensor. But it is very important that what I observe that I is up. See the x bar coordinate up, and the other is down. Now, how I check whether this transformation law is okay? Look, if I cancel r with r, imagine, but just by imagination, there's not cancellation. Just by imagination, these are cancelled. I am left with I, r. So this is coherent. Okay, this is coherent. If I just cancel these, I get I here and I here. So in fact, this is coherent. This is a check. If you want to check, if you write an equation and you want to check whether it is right or wrong, this is the way to check. Now, I talked about contravariant tensor. I will talk about covariant tensor. Covariant tensor is the most important tensor used in geometry, and I will explain to you why later. Now, the transformation law for this tensor, look here, I don't know if you can see this. Down. This is the covariant tensor because I is down, it is covariant. And this bar here, this is a covariant tensor of first order in the bar coordinate system. This is a covariant tensor in the unbarred coordinate system. And this is transformation law when I move from this coordinate system to that coordinate system, and you can see. Look here, the R are up, whereas here the bar is up. Here the bar is down. See, the bar is down, and here the bar is up. So this will show you the difference between these two. Again, if I have these cancelled, I will get I, R. I is down and I is down. So in fact, this is a check. What if I write this equation, I can check it whether it is right or wrong by this imaginative cancelling of indices. Now, we talked about first order tensor. Of course, I can have second order, third order, fourth order, or n order tensor. Now, the second order tensor, you can see here I have two numbers. Now I have two numbers. Two numbers means I have second order tensor. Now this is happening, this is up. So this is contravariant. So this is a contravariant second order tensor where in the x bar coordinate system. This is, look, this one is RS, two numbers. So this is a second order tensor, okay, and it is covariant because these two numbers are up. Now transformation law, the same as we did before. Look, I with R, J with S. I from the bar to R from the unbarred coordinate system, and the j from the coordinate system, from the bar coordinate system to s to the unbar coordinate system. So this is how we write the transformation equation of second order tensor. Covariant. Contravariant. Now this one, this is covariant. Why it is covariant? Because the two numbers, I and j, are down. So this is the notation of a covariant tensor. And this is in a bar coordinate system. This is also a covariant. And this is in the unbar coordinate system. Transformation law, the same. Now I look here, I go from here to there. Here I go in the other way. R to R, R to R, and S to J, S to J. See, the bars are down, here the bars are up. This is a covariant tensor. This is, of course, one can ask me, can we check? Look, RS cancelled with RS. I am left here what? IJ. Here I have IJ. So this is a test, a rapid test of my equation, if I am right or wrong. Here the same, you can see RS with RS, I am left with IJ and here IJ. So in fact this equation is right. Now of course, I can have the mixed tensor. Mixed tensor, look, here I have a tensor in the bar coordinate system, but I have I is contravariant and J is covariant. So in fact this is a mixed tensor because it has a contravariant component and a covariant component. Transformation law, for the contravariant, I have the bar above and the other low, down. Whereas for the covariant, I have the S above and the J below. So in fact, this is a transformation law of a mixed tensor of the second rank. Second order. So this is a second order contravariant tensor. Of course, I can have arbitrary tensor. Look at this tensor. This tensor, this relates a tensor and the bar coordinate system to a tensor and the unbar coordinate system. The bar coordinate system, this I1, I2 to IP. So in fact, this is P times contravariant, and these runs from J1 to JQ. So this is Q times covariant. So this is a mixed tensor, which is P times contravariant and Q times covariant. And of course, I can write the same way I did here. I can write the transformation equation. Now I will go to a quantity which is very important in general relativity. But let us look at the classical idea of this quantity. This quantity I call metric tensor. But we will see more about it. And we will find that metric tensor is an essential element in general relativity. But for the time being, let us see how we go about it. I start by classical distance between 2 points. If I have point A and point B, how can I find the distance between point A and B? The answer is using figure of theorem. Okay, x1 squared plus x2 squared plus x3 squared, and then square root. So this is the idea here. But look, I multiply it by GIK. This is what I call a tensor. We will see what that means later on. But here, if I take this equation, okay, I make this Ij equal to 1. Okay, so this will be the same as delta. And I will have x1, x1. Okay, so this is square plus 2 squared, 3 squared, etc. And can be given by this expression. And finally, I can write this expression. Look at this expression, it's very important here. The only thing, I put ij. ij, when I equal to j, this is the same as this one. So dx will be squared. Okay? So I equal to 1, j equal to 1, I will have this one, x1 squared, I equal to 2, j equal to 2, squared, etc. Not in general. In general, one can say, here squared, not squared, not squared. Can I have something different? Can I have something different? The answer, yes, I can have something different. In that case, I use this symbol, GIK. In fact, you can see this is a generalization of this. This is only for ij are equal. If ij are not equal, I will have terms. In addition to these terms, I have a term of dx1, dx2, or dx1, dx3, or dx2, dx3. How I can express it? By this expression here. Now, ds squared, this quantity, ds squared, has a name. It is named line element. And if you ask me what is the most important term in general relativity, I said the line element. The line element is the distance, how I measure distance between 2 points. And this quantity here, I call it the metric. The metric. So in fact, this line element can be written in terms of metric. And this equation is very general equation. I can have ij equal to anything, but you have to remember that ij, if they are different, this is not zero. Delta ij, they are different, it is zero. Here, no. Here, no. This is generalization of this. Now, the metric tensor, it exhibits many characteristics. First, it is symmetric. That means Gij equal to Gji. G is non-singular. That means the absolute value of G is not equal to 0. The distance concept generated by G is invariant with respect to the change of coordinates. Oh, this is very important. This is very important. If I change the coordinate system, G remains the same. And in fact, we discovered that this is the currency of all tensors. Tensors are invariant when changing the coordinate system because of something that I will explain in the coming lecture. Okay, let us go on. One of the most important thing in tensor calculus is raising and lowering of indices. And you will have in future lectures a lot of algebra, how to raise or lower an index. Here you can see I have an index. This is a contravariant vector. This is a contravariant vector in the xi coordinate system. Okay? I multiply this by g gamma beta. See, beta as if it is cancelled. It's not cancelled, but look at it. I am left with alpha up and gamma down. So in fact, by multiplying by the metric tensor g gamma beta, I am lowering one of the indices. Okay, so it is lower. I have one index lower and the other remain up. So in fact, here I am getting a mixed tensor. Here I have covariant tensors, and here I have mixed tensor, and this is called, this process or this operation is called lowering of indices. I can do the same. Instead of multiplying by G alpha delta, I can multiply by G alpha delta up. So if I have a tensor, which is gamma delta, I multiply it by this. Look, delta will cancel. I will have alpha gamma remaining. This is always a check. The indices which is repeated, they are cancelled in imagination. It is not a real. I am left only with something which is coherent. Left is coherent with the right hand side of the equation. Now, if you tell me, what's this? I tell you, I can write a book about it. This is what we call Christopher symbol. What is a Christopher symbol? Has a Christopher symbol anything to do with gravity? How do we define a Christopher symbol? I will just start by defining Christopher symbol and give you an example of how to use it. Okay? But in the coming lectures, I have to explain how it is related to gravity. But here, let us see. Most important thing to check whether this Christopher symbol is a tensor or not a tensor. And what is the implication of being a tensor or not a tensor on the field equation? This is a very important point I have to explain and to derive now. I want to see whether this quantity is a tensor or not a tensor. You will ask me, how we can check that a quantity is a tensor or not a tensor?
We'll do a transformation.
Exactly. If it obeys the transformation law of a tensor, it is a tensor. If it doesn't obey the law of transformation, it is not a tensor. So how we define this? Look, I have in fact two types of Christopher symbols. This is, I call it of the first kind. Of the first kind, I have here 3 letters, and 3 letters are down. Okay? 3 letters are down. And this is defined by this relation. 1/2 partial by partial xi, partial by partial xj, partial by partial xk. Look here. There's a minus sign. So I have 1 plus sign, plus sign, minus sign. This is a definition. Don't ask me why this is negative and that is positive. This is a definition. Okay. Now, the question is, can we simplify this notation? Can we spell? Look here. The answer is yes. I will replace this partial by partial xi by simply xi. See, I will take this one. This is partial by partial k, and this is minus. Partial k, I put the k here, the third letter. So this quantity means partial gik by partial xk. This means gjk partial by partial xi. And this one gki partial by partial xj. Okay? So in fact, this is how we read this. So instead, this third letter is the derivative. Instead of writing this way, I can simplify this way. Okay? So in fact, this is a notation. This is a notation. This is a simplification of the notation. Instead of using the partial derivative, I simply put the last letter to stand for the partial derivative. Now this is an example. Let me go through this example, and you have to make I will give you as a homework to see how this works. Now in this example, I have a spherical coordinate system defined by this matrix. Spherical coordinate system defined by this matrix. I will use this definition as a guide. Okay, this is nothing to do with the problem. I'm just using this as a guide. In a matrix, you have the components of a matrix: G11, G12, G13, G21, G22, G23, etc. Okay, so I will use this one as a guide. Now, what I observe, looking at this, G11 constant is equal to 1. G22 is equal to x1, 2. Look, what is x1? This is not an exponent.
Theta.
This is x1 is the coordinate. Okay, this is the coordinate system, and this square, this is exponent. So this one is not an exponent, whereas this one is exponent. That is why I'm putting it between brackets. Here the same. This x1, 2 is exponent, whereas x1 here. What do you think? This 2 is exponent. This 2 is for the coordinate system. Okay. So don't confuse the exponent with the coordinate system. So in fact, the G33, which is this one, is equal to x1, 2, etc. Now,
دكتور سؤال ممكن سؤال في السلايد اللي فات ليه حضرتك جي 1 2 جي 1 3 وكده اللي هي جي اي جي حضرتك كنت في السلايد اللي قبلها المودولس كان از نوت ايكوال 0 ليه هنا حطيناها 0؟
لا الاي جي فهمت القصه. الاي جي يوجوالي في الجنراتيفيتي ما عدا التريس الباقي زيرو. راح نشوف examples. Not always. We will see examples, especially when we talk about the general tensor. These terms are not necessarily zero. Okay, now I will answer this question in the coming lecture. Very important question. Now, look here. What I did. G221, that means G22 with respect to x1. Okay? If I take, of course, G111, this is 0 because constant. Okay? Now G22 with respect to x1, 2x1, 333. Okay? I have this quantity, 2x1. This, because this is partial derivative, okay? This partial derivative, x2, etc. This is not the question. This is easy. Now I want to determine the gammas. Which gamma is equal to 0? Which gamma is not equal to 0? So in fact, I have to find out a method to list all the gammas and then check one by one which one is 0, which one is not 0. The one which is 0, that means it doesn't contain these terms. If gamma contain any of these terms, it will not be 0. It contains at least one of them, it will not be 0. It will be 0 if none of these terms are present. So how I go about? Look, I said G11, I am putting here and out. This is nothing to do. That means this is just a guide. If I have gamma 11, I have gamma 11 with respect to 1. Gamma 11 with respect to 2. Gamma 11 with respect to 3. For example, if I have G23, I will have gamma 23 with respect to 1. Gamma 23 with respect to 2. Gamma 23 with respect to 3. Of course, this third number here is derivative. Okay, derivative with respect to something. So in fact, if I do this, for example, gamma 22 with respect to 1, I will get these quantities. Now how I get these quantities? In fact, I take the ijk for each gem and I manipulate it, and I will get these quantities. Okay? Now, for example, this one, I have to go back and see which one. 221 is not 0. Okay? So here I have 221, this is 0, this is 0. I am left with this one. Okay? I am asking you to go at home and do this exercise. Okay? Go at home and do this exercise. You have my notes. And do this exercise. It is very interesting to identify which gamma is equal to 0. Of course, this is just an example. But when we talk about general relativity later on, the solution of the field equation, in fact, there's an intuitive way to check whether a Christopher symbol is 0 or not. And this is very important, Jaleel, to identify whether a Christopher symbol is equal to 0 or not. Why? Because you will see that the field equation is calculated entirely in terms of Christopher symbols. Mm-hmm. So any solution of the field equation requires to know how to differentiate, how to know that a certain Christopher symbol is equal to 0 or not equal to 0. Now I'm using just this quantity here. If I take ijk and I make permutation, I will get this quantity. This also you can make it as an exercise. You take ijk and you take jki and you add that, you will end up with this quantity. Okay. Now, I have to answer the question whether the Christopher symbol is, in fact, a tensor. And we said, what we said, if it is a tensor,
it has to transform as a tensor.
It fulfills the transformation equation. I will start with this. What is this? This is G, okay, and the bar coordinate system related to G and the n-bar coordinate system, and I am using the transformation equation, okay? Again, R with R, S with S, and I'm left with IJ. This is a check that my equation is right. Now what I will do, I will take the derivative of this equation, okay? So normal derivative, you know, first it's derivative, the second, etc. First constant or derivative of the first multiplied the second, etc. This is normal calculus you can do at home easily. How to derive 3 functions. Okay, I will get this. And also I can use the chain rule for this quantity here. I will get this quantity. Now, look, I take the equations we just seen and I write them in this way. I write them in this way and I add them. Why I write them in this way? I write them in this way because I have, see, I multiply by minus here. I write them in this way because if I add these three, I will get the Christoffel symbol. Okay? If I add these three, this is a Christoffel symbol and the bar coordinate system. And this is, I don't know. This is too many terms. If I look carefully at these terms, in fact, some of these terms will cancel. And I'm left with this. If I add these, I'm left with this. So in fact, these three are the definition of the Christoffel symbol of the first kind in the bar coordinate system. This one is the Christoffel symbol of the first kind in the n-bar coordinate system. And this is, what is this?
Transformation law.
This is transformation equation. This R with I, S with J, T with K. So in fact, this is a transformation equation. There is something strange here. There is another term. So in fact, what I discovered,
It does not transform as a tensor.
it does not transform as a tensor. So Christoffel symbols are not true tensors, or they are not general tensors, but they have
Properties.
some property of a tensor. They have some property of a tensor, which is this term here. Therefore, I call them affine tensor. أحد يعرف كلمة affine بالعربي؟ affine.
حاجة ليها علاقة يعني حاجة علاقية.
صح. تآلف بالعربي تآلف. تآلف يعني يتألف من شيئين. يتألف من جزء تنسر وجزء غير تنسر. Okay. So تآلف. Okay. It is affine tensor. So in fact, this is very important that the Christoffel symbol is not a general tensor, it is an affine tensor. And this is one of the most important properties that we have to discuss in the coming lecture. Now, of course, we talked about Christoffel symbol of the first kind, IJK, but the most important tensor we are going to see generally is this one. Christoffel symbol of the second kind. Look here, what I have. I have one of the indices is up, and two indices are down. Okay? So this is in fact Christoffel symbol of the second kind. And how I obtain this? By raising one of the indices by multiplying by the metric. If I multiply by the metric, I have one of the indices will go up. So this is called Christoffel symbol of the second kind. And all our work in generativity will be using this type of tensor, Christoffel symbol of the second kind. Of course, once again, transformation equation consists of two parts. One part transformed like a tensor, plus an additional term. So in fact, this is also a affine tensor. It is not a real tensor, it is a affine tensor. This is an important formula because I want to use later on. I will not derive here. You can derive it easily from this part. Now, also, let us answer this question. If I take a derivative of tensor, is the answer is a tensor? If I take a derivative of a tensor, is the answer is tensor? Taking a derivative of something is what?
It's
No
tensor.
Okay. So the question is, if I take a derivative of tensor, what I want? Look here, derivative of this multiplied by this plus derivative of this multiplied by this. Is this the tensor? The answer is no. The answer is no. This is not. This is not a transformation equation of a tensor. So in fact, if I derive a tensor, I will not get a tensor. Is there a way to make things easier and we can have lunch?
We'll define a new derivative.
Okay. This is I did the same for covariant differentiation. I will not go into all this. You can find in the sheet. Okay. I am just making a manipulation, and I am using the term which I said before. I am using this equation again, and I am left finally with this. Look, this is differentiation of a tensor. This k here, that means I am taking the derivative with respect to its k. Okay? Look here, I will get this term. So in fact, this quantity here is a tensor because this quantity transforms like a tensor. This quantity, I call it covariant derivative. Covariant derivative, we will see more about it. What is the meaning of covariant derivative? This we are going to discuss physically in a coming lecture. So my answer is, if I take the derivative of a tensor, the answer is not a tensor. But I can add term such that it transforms like a tensor, and this term plus the original tensor I am adding to by itself, it transforms like a tensor, and this is called a covariant tensor. Quiz. How much you left? Okay. What is this? Free index. And what's this? Dummy index. IJK. Chronicle delta. Okay. When they are equal to 187. How to compute 0, 0, 0, 1. What is here? 0, 2. Okay, so you know how to handle a matrix. Okay, here, what is this? This is transformation equation from part coordinate system to unpart coordinate system. This is notation. What is this? This is first order contravariant tensor of that is it. And what's this? This is the same, but in the part coordinate system. Okay, what is this? This is transformation equation of a tensor, of a contravariant tensor, from the part coordinate system to the normal coordinate system. This is the same, but for covariant. And this is for second order covariant tensor in the part to the unpart. What is this? Of course, you know. Super symbol. What's also important here is the sign. And how we can write this? We can write it K, I, J, and this K, what that means? Partial with respect to K, partial with respect to I, partial with respect to J. And here, this transformation equation of Christopher symbol. It consists of two parts. One part is transformation of tensor, and the second part, which is an additional, that is why it doesn't transform as tensor, we call it affine tensor. And what is this?
Raising lower.
This is, I have a tensor, I multiply it by the metric, and I have one of the indices is lower, so I am lowering an index, and here, okay, I am raising an index. So in fact, all what I want you to know from this lecture is this simple. Is this simple? Is this simple? Okay. So I will stop here. I will stop here, and I'm sure that you are hungry. If you are not hungry, please ask me. In fact, I want to explain what we will see. This is not a symbol. شوية بجعلس. When you go to the physical meaning, this is mathematics. But when you go to physics, so my next section, what is the physics of this? What is the physics of math? What is the physics of Christopher's? Okay, how we can move from one point to another point in general space-time, not flat space-time. Okay, so all these things we will discuss during the meeting. Thank you very much. Thank you.